A very warm welcome to everyone from IT Next in association with Emerson. We're really glad to have you here today, and thank you for joining us. So today's topic is building green data centers. Now this discussion will cover areas on how best to build energy efficient data centers, understanding how companies can reduce their carbon footprint, and how the Indian enterprises are looking to adopt new emerging technologies. So today's speaker is Mr. Vikas Dubey, who is the National Sales Manager for Data Center for Emerson. He has over 18 years of experience and has been with Emerson for the past 2 years. He has also worked with PCS Tech, Infinova, ECIL, Repiscan. He's experienced in data center consultancy, audit and design, constructions, operations and maintenance, business continuity planning, and and he's also an electronic systems security expert. Thank you, and Mr. Dubey, if you can take over.
Yeah, thanks, Varun. Hi, everybody. Good afternoon. I am Vikas. So, our topic for today's discussion is green data center. As you know, go green is the buzzword today. However, our discussion is focused on the green data center. We at Emerson Network Power, we manufacture almost 60 to 70% of equipment which goes in DC infrastructure. And we, as a leading manufacturer and turnkey data center builder, we have few recommendations on green data centers, which we are going to touch upon today. So I go with some basic information on data center and what is green data center. So as you know, the green data center is basically wherein we do storage of our management, and then data store where lighting, electrical, and computer systems are designed, which gives you maximum energy efficiency. One definition by encyclopedia. Second definition by IBM, which says a data center is constructed to as possible. All computers and lighting systems. So where the green word comes in, how much we are taking care of the earth, or maybe economy, or maybe how we are using recycling and improving health of quality of the system. That's where the green word comes out to be. So there are again some few things which is very known commonly to everybody, which is like global warming, greenhouse effect, or we are concerned a lot about ozone depletion layer, which is in last approximately 6 to 8 years, this has been discussed a lot. We have Montreal Protocol, we have different discussion on different platforms, wherein we discuss there's a huge issue about ozone depletion or greenhouse effect, but how much we are concerned about it and how much we are doing to manage all those things is a big question. It's a big question mark today. So here, as a manufacturer of IT infrastructure, Emerson again do a lot research on those topics. And based on our experience with data center build and consulting, we have come upon some ideas or some small things which, if you take care or if you take in consideration while designing or while going for new data center or maybe co-location, it helps a lot. Again, I will discuss the challenge and solution. So what is the challenge statement for green data center or green today? The challenges basically are data centers are in breaking point. What I mean to say here is the load or per square feet of load, electrical load is going very high in case of data center. So we talk about high density load, which is typically one rack going for 10 to 15 kW of load. And then we are struggling for power. The cost of power is going very high. Density goes up again every 2-3 years. The density is going very high. The computing power is very strong. At the same time, we are putting a lot of chips within a small area. So my density or my heat load dissipation which goes very high. Cost of energy outputs going very high. Here the biggest problem is we are using most of the power for cooling of the equipment. For example, if I have to pull X capacity of equipment, I have to use 2X amount of power, which is the question, and which is where we have to hit upon today. What probable solutions are there to handle all those situations? One, the largest solution is we need to leverage the energy efficient products, be it a cooling, be it power, be it electrical systems, be it electronic security systems. Any systems we use for data center construction, it has to be efficient system. But then we know a lot of these words like recycle, lease, remarket, refurbish, but how much we use it, again big question mark. So we have to take all these things in our day-to-day life and consideration while deciding big numbers for capex or opex for the company. So lease, recycle, reuse is the buzzword again. We need to use the modular design. We should not construct data center for future which is huge, and we may require something which may be down the line 2 or 3 years. We construct something modular which we can build or we can make as we grow. So for today I need a demand for say 13 kW or 50 kW, so I make say 10 to 15% higher size. That's it. We should not go for double or 3 times more than the requirement of today. So modularity is the biggest requirement. And then the best practice. When I go down the presentation, I will discuss what all best practice we should use. So how we control or how we manage the green data center? One requirement or one panel is that for the PUE. PUE is basically power usage effectiveness, which is nothing but the inverse of efficiency. So when we do the ratio of total electricity consumption in facility, which is divided by the power which is used for electric consumption, gives the PUE, which is basically reverse of the efficiency. Idle PUE today's world, we normally look for something which is below 1.6. Normally data center typically runs a PUE which is around 2 or 1.8. Even we have seen data center as of today running on 2.8, even more than 3, which is again a big question mark. Then we have categories of 0, 1, 2, 3, which depends on which point of source we are measuring the PUE. If I am measuring it on my server level, which is at category 3, or category 0, which I am measuring at the power source level. So there are different categories for PUE measurement. But our target at least should be something between 1.5 to 2, which is the practical and achievable also. Now the next slide shows about the power usage of data center. How much power goes for what? So if you can see on the right side of the slide, the IT equipment only takes 50%, which is very surprising. 50% of my energy I use for infrastructure, and out of that 50%, the cooling takes 25 plus 12. If you can see on the left side of the pie chart, so air movement 12% and cooling is 25. So overall 37% of power is devoted to cooling, which is again surprising. So if I control my cooling power or cooling power equipment efficiency, I control energy consumption a lot. The other portion is small, like transformer, electrical portion, and then the lighting. So which is 10 and then flexible percent for lighting. So here big question mark is the cooling efficiency, equipment of the cooling equipment efficiency. So Emerson being manufacturer of cooling equipment, precision air conditioners, we are going to discuss a lot about which type of equipment we use and how we reduce the power consumption which is 37% of the total power in the total data center consumption. Again, some small questions: how and what we can do to make data center green. As you can see, we need to optimize a lot of things like room cooling, efficiency of cooling units, the way air flow is managed, the way you have kept the racks in the data center, then cooling at the source of the heat. Peripheral cooling or perimeter cooling is again a big question mark these days, so we are going within racks. Even Emerson has done something about it. We are creating some smart solutions, which is a data center in a box. So now perimeter cooling is a big no. If you discuss typically about data center, which is talking about 30 to 40 kW of range. Then we use economizer for free cooling. Size the power system for optimized efficiency. So there are small steps which we do for making data center green. This is a slide which shows the energy logic, the cascade effect. So if I am saving 1 watt at server level or the endpoint level of the energy gen, I am saving almost 3 watts at the source level. If you can see how the cascading effect happens, so saving at server component level is must. If I am saving there, it is going at least 3 times to the power generation level. So at switchgear and transformer level, I am saving 3 watt typically. If I am saving 1 watt at the server level. So what we do for this saving, which I have shown in the last slide, there are two things. Again, you might have heard of virtualization and consolidation. How we do it? It's very simple. On the left side of the slide, if you can see, there are three systems which have got 1 kilowatt load each, and they are busy 10% of time. Overall capacity of the data center is 44 kW, which is utilized at 75%. If I consolidate and make a single system which is virtualized on a single platform, and all those applications 1 to 6 running on the single virtualized system, so my total consumption goes down from 4 to 2 kilowatt, which is 50% less. Capacity of data center is same 4 kilowatt, but I am utilizing it 50%, and system is busy a little bit more. It is around 35%. In the bargain, what I am doing, I am saving power. So this is one of the typical examples how we can save energy by use of virtualization and consolidation. Again, while choosing your chips or microprocessor or the equipment which runs your applications, you have to be very wise. The type of efficient chips you use, like you can see in Intel, they have got some chips which they claim to offer 60% faster performance within the power envelope. So again, you have to be very wise while you select your chips or equipment or hardware for applications which is running on your system. So this is again one part of it. Now it's very, this slide is very interesting. If you see, you select the equipment which is nameplate rating of higher efficiency. I have given two cases over here. Equipment A, power supply A, which is 91% efficient, power supply B, which is 93% efficient. If you go by the graph and typical uses, which is percent of full load, I don't use any equipment at full load. It's well known, well be designed. So we use the equipment on 10 to 30% loading. You can see the shaded portion. So the nameplate rating, which is got on the for model A, which is 91% efficient, giving me more efficiency on the shaded region, which is 10 to 30%. So the equipment which has got lower nameplate rating gives me more efficiency because I am operating the equipment at lower load level. So while selecting your equipment, you have to be very careful that what is the efficiency of equipment at lower loads. Of course, at the higher loads, the nameplate rating of higher efficiency gives you more efficiency, but it doesn't matter actually because I am operating the system at very lower loads. We never go beyond 50% in fact while we design. So 10 to 30% is the optimum level. So you have to make sure if you are checking the nameplate rating of the power equipment, it has to be on higher efficiency on the shaded region, which is 10 to 30 or maybe max 40%. This is again one of the small criteria you consider while purchasing or designing your equipment for data center. Again, small thing. You have to make sure the room is properly sealed, there is no leakages, so we can avoid short circuit of the heat and heat current loads. Vapor sealing is must. So what heat I am producing, it is to be heat which is generated by the hardware only, not by the vapors. So we need to seal the hot aisle, we need to seal the cold aisle. We will discuss cold and hot aisle containment in the coming slides. Again, this is one more slide which shows the difference between comfort and normal the cooling what we do for machines. So precision and comfort cooling, what is the difference? In precision area, the 95% of the heat is sensible heat, which is generated by the hardware servers, and very small portion goes for the latent heat. Other way around, in comfort cooling, the latent heat is a major portion, which is 30 to 40%. So in precision EC, normally what we do, we try to control the sensible heat, which is 95% of the total equipment. How we optimize the room cooling system and temperature? One option could be you replace your old cracked unit with new, which is more efficient, and you are doing capacity modulation. Capacity modulation is nothing but requirement of cooling based on the demand of your equipment. If your equipment demanding more, you give more cooling. If demand is less, you give the less cooling. By doing this, I am saving a lot of energy. We can reduce crack temperature setting Again, actual recommendation is between 17 to 27 degrees centigrade. So my data T is high. Difference in temperature is high. That way again I can have more efficiency. These days the chips manufacturers again they are recommending higher temperature. So we should not go for typical 22 degrees plus minus 1 in data centers. We are talking about openly now 24 degree, 25 degree ambient in data centers. That way we have to design the system accordingly. Preventive maintenance. Again, this is one most important thing. While in case of a data center, once we install system and it's operational, normally we neglect the maintenance. Again, this maintenance neglection is again gives you a big problem from the point of view of efficiency. So the proper charge and pressure should be checked periodically in the AC machines. Air filters should be cleaned regularly at regular intervals. The coil, compressor and evaporator coil should be cleaned. And you have to use the BMS system, building automation system, or damper control again based on the load on typical rack. If you are feeling there is a hot spot, then the cooling should be directed to that area, not to other rest of the area. So I am cooling economically, and I am not wasting my cooling power. So how we do it in immersion, how we use this cooling wisely to save the 37% which we discussed in the earlier slide, which is the major portion of energy consumption in the case of data center. So what we do, we use variable capacity compressors. The approach is how we do it approach basically in variable capacity. We use multi-stage compressor, we use digital scroll compressor, or we use flexible cooling. What we do in digital scroll is based on a requirement of my servers and demand of servers, I modulate the capacity of my cooling, and by doing so, I use less energy and ultimately saving in the operational cost of the cooling. Again, we don't use any CFC substance, which is again problematic to ozone layer. So what substance we use normally R22 and R407C. 22 is again being phased out. So you can see the comparison in the table, which is like 407C has got the less global warming potential, more greener, having ODP 0, which is again recommended. So now R22 is being phased out. R407 we are using as a refrigerant. So this is 407C is basically phasing in now. Yeah, this is one of the slides which is very important, very useful if you discuss about the control of power in case of cooling. The approach is hot aisle and cold aisle approach. So what we do, we try to segregate the cool and hot portion of the data center server room. By doing so, what I am doing, I am avoiding the mixing of cool and hot air. So once hot and cool air is separate, it makes my data center more efficient. You can see the thermal profile on the bottom of the slide, which shows the cooler regions on the lower portion of the rack and the hot spots on the top portion. So back to our front rack placement is exposed server to top of the rack and overheating. So how we do it, how we mitigate this problem? By doing hot and cold aisle alignments. So if you can see in the bottom portion of the slide, what I have done is, on the first rack it is a hot aisle, in the center it is a cold, then again hot aisle, cold aisle and hot aisle. So what I am doing, I am separating cold and hot portion of the data center. By doing so, I am containing my cold area in one location and hot area in one location. There is no mixing of the air. By doing this, I am again saving my energy which is used for cooling. So this is hot and cold aisle approach. This is one more interesting slide which shows about the rack arrangement. If you can see in the left side, the crack units are kept on the left side, 2 crack units. In a typical room scenario, this could be 2 crack or 4 crack on the either side of the room. In this slide, I have shown 2 crack units on the left side. So once I am using this cooling technology, hot aisle is in front of the crack unit, and the cold aisle is in the side. So what I am doing is I am flowing the air from the cold aisle, and the return air is coming from hot aisle from the top portion of the racks, and again sucked in by the crack units. So what is happening here in the left side, the length or maybe velocity I am using at the full. On the other side, if you see on the right side of the slide, the crack units are placed on the other side, at 90-degree other side of the room. So the velocity is going very less. I am not able to capture the hot air properly, and while again at the same time the cold air is not going at the last row of the rack. So there is a problem in the alignment. So preferred alignment for the rack and crack unit is the left side. On the right side, this is a problem in design. So I am utilizing this design for maximum airflow and efficiency of my cooling unit. Again, how to optimize the airflow within the room. If you can see in this slide, the center of the there are 4 row arrangements, and the center of the row you can see the cold aisle, hot aisle in the again either side, and this perforated tile you can see in the center. So this hot aisle and cold aisle approach, again you are showing the path of the flow of the air. You can see the air is thrown from the perforated tiles from the bottom of the floor. This is a raised floor. It is basically sucked in by the servers and units. The hot air goes on the top, which is a natural phenomena. The hot air always goes up, cold air goes down. We are using the natural phenomena, and then it is sucked again by the crack unit. So this cycle is complete. So this arrangement of hot and cold aisle basically I am utilizing to make system more efficient. Again, if you go one step further from this, we block hot air recirculated by using blocker panels in any excessive space between the racks. So what I am doing basically, I am stopping the hot air coming back to the system and then avoiding the short cycling. There is some gap between hot power racks, high power racks and low power racks. Again, we have to make them separate. They can cause significant infiltration of hot exchange air. So again, we have to avoid the short cycle of the air and mixing of cold and hot air. So there are different arrangements to be done. We use blocker panels. This is one of the best practice. Blocking the panel. Wherever I am not putting my equipment, I have to block it by putting the blanking panel. Again, by doing this, I am avoiding the mixing of cold and hot air. Again, within the room, how we do it? Placing high kW racks in the center of the room. Suppose there is a crack units on the either side of the room, on the left and right side. So the wise thing is to put high kW or high density racks in the middle. The reason is, by the time the center of the room is cooled, which is high density racks, which will again produce the heat will be sucked by the PAC units. So the cycle of collecting the hot air to the PAC unit is complete. If I am putting those units on the either side of the room, the cool air is sucked initially by them, and the cycle of the air will be not complete. So it is wise to put the high density racks or high density equipment on the center of the room. If PAC is installed on the either side of the room, or if PAC is installed on one side of the room, then your high density equipment should be on the extreme end of the room. So again, I am making my hot air cycle complete and avoiding the mixing of gases, making system more efficient. The return air is on higher side, again 27 degree, 28 degree, which makes my cooling units more efficient because my delta T, which is the difference in my cool air and hot air, is higher. So again, which makes my system better, efficient, which gives you less effects. This is one more typical arrangement of how we place the perforated tile. So if you can see on the bottom of the slide, you should never place the perforated tile just next to the cooling unit. If you can see what is happening, if I am putting my perforated tile just next to the cooling unit, there is a problem of airflow. There is a negative flow over here, and you can see the air is being sucked again from the just before the first row of the rack. So my cool air is being thrown from the bottom of the floor, and because I have put one tile, perforated tile just before the PAC unit, which is creating the negative pressure. So first ideal location to put the tile is here between the first row, and then as you go down, you can keep on placing the perforated tiles. So what happens as you go away from the crack unit, velocity decreases and pressure increases to maintain the uniform CFM. So basically you have to avoid putting the perforated tiles very next to the crack unit. The ideal location is after first row of the rack. You have to start putting the perforated tile. Again, this is biggest problem and biggest challenge when we do refurbishment or we do the quality check of the system or data center which is already installed. Because the growth of data center happens in haphazard way. A lot of things goes below the floor. Sometimes even the tile comes up on the data center because of the pressure of the service equipment. You can see the cable trays and then water pipes, a lot of infrastructure. Structured cabling, your power cable goes below the floor. Initially we designed for some 300 mm or 400 mm of post floor. During the course of installation or course of addition of servers, the data center floor is filled up with all those things. So there is a problem because my PSC unit is not able to throw the cold air or the CFM is reduced. So basically what we have to do, we have to reduce underfloor obstruction. Planning should be very good. So we have to plan for next 4-5 years what all systems will go below the floor. Accordingly, we have to start, we have to make the floor of data center. To start with, I recommend 450 mm is the minimum for typical load of 30 to 40 kW. With higher loads, then we go for 500 mm or even 1 meter. It all depends on the load basically. So what happens, if you can see in the bottom of the slide, the cool air is being obstructed and again being returned to the equipment from where the cold air is being thrown. So that's a problem and we are losing the efficiency of the machine. In this chart you can see how the raising of the floor height goes with the higher density of the server. So as you know, we increase the density of the racks which goes like you can see in the x-axis which is 1 to 8 kW. Same way the raised floor height goes. So it should not be other way around. In case of higher load, the raised floor height should be higher, of course. It should not be lower because we are creating a problem. If you can see on the right side picture, there's a lot of mess. It is a mixture of lot of power and structured cabling there below the first floor, and there's a big obstruction. So this system will never work as an efficient system, and I'm losing my POE. I'm losing my efficiency of the system. This is no way green. So as and when you keep on adding the power or you can keep on adding the kW of the system, you have to raise the height of the first floor. If you can't do it, then you have to do for refurbishment or maybe with a new data center which has got requirement of some good height or good requirement of data center floor height. Again, how to stop my mixing of air by sealing. So we have to seal all the openings. Seal all openings, the raised floor, subfloor or perimeter walls. Normally we have seen when we do the first floor, the perimeter area is never properly blocked. There are a lot of leakages. So that is again we are calling for less efficient system. Normally we have to avoid all those things. You can see over here how the openings for cable and all which is properly sealed on the bottom of the slide. So I am avoiding again the cool air coming out from the first floor. How to avoid the hot air recirculation in the rack? We need to block hot air recirculation by using blanking panels. You can see the below of the slide. You can see there are two pictures. There are two ways to do side view of the rack. So we need to put the blanking panels wherever there is no equipments are installed or there is a space available. We have to put the blanking panels. So my circulation of air is uniform and there is no mixing. The blanking panel will avoid the flow of cool air wherever it's not required. It will only be sucked by the server equipment where there is a hot spot or where there is a requirement of cool air. Other areas will be blank. If you can see the two areas on the right side of the slide. Again, if there is obstruction, there is a problem. What we can do is we can install some fans. Additional cooling we can do. We can draw air from the back. There is some suction fan we can use to pull the hot air again and then make this cycle complete. One more way of optimizing the airflow within the racks, we can expand the rack depth. Expansion channel we can provide. What we can do, we can use for cable, we can use for cooling, we can use for the equipment. Those expansion channels basically utilized for your cable dressing. You can see on the left side there's a mesh of the cable which we can straighten when we use this optimized airflow racks, wherein the length is increased by say 20 mm, 25 mm based on your again requirement. It also depends on the application, what type of industry you are in. If you are in telecom or you are in an industry where a lot of structural cabling is required, so you have to use this expansion panel, which will basically increase your rack depth. Again, by doing this, I am channelizing my flow of cool and hot air. There is no mixing, and my system is more efficient. Now I'm coming to the power system. Power system, again, what type of UPS should I use to make system green and more efficient? So again, there is a question of what type of loading we are giving. If you can see in this graph, efficiency versus load. The maximum load what we use is again on the range of 20-25% or max 50%. So UPS rating, if you can see, if I go by the rating, the type of saving I can do per annum. So what you have to do, you have to choose your efficiency of the system rating which is given on the nameplate very wisely. We should never go for equipment rating which is very high efficient, but we are not using that type of efficiency. So optimum range of efficiency, you have to check what type of efficiency, what type of loading we are doing by checking your loading sheet or loading pattern of equipment in the future and the present, and then you decide equipment rating basically. You have to use the high power factor equipment. Again, it will cut down the losses. Reducing the electrical pollution, which is the harmonics. So we have to use different type of equipment for that. We use isolation transformer at required places. The isolation transformer again, it reduces your harmonics and reduces cut off the electrical pollution. Again, we can use low total TSDI equipment for UPS.
Nice.
Then we can basically use less battery bank.
Okay.
I am adding batteries and I am adding basically more lead to system, which is not green. So number of batteries again we have to choose wisely based on the number of minutes we use for backup. So we have to use batteries again on the requirement if I am using common battery bank or individual battery bank. So normally people go overboard while designing the battery system. So we have to be very careful what type of like 30 minutes requirement is there for backup. I have to use the battery bank, which is common bank or individual bank. So those things you have to take care while designing. There are some standards. One is green grid. Emerson is also a member of this green grid. Then Energy Star ratings 4.0. IGBC. IGBC is nothing but Indian Green Building Council, which has got some standards. There are very small things when we make data center we have to consider. Like if possible, we can grow vegetation on the roof of the data center if possible. This is very small thing, but again it cut down to your energy cost, or it cut down to your waste of energy. While designing again, we have to have some requirements on data center wherein we can save energy. So some LEED certification, we have got LEED requirement of different ratings. So many small things we can do while designing data center, which is recommended in the LEED. By this, my presentation is over. Thanks a lot everybody for your time, and I look forward, maybe we can share this contact details and all. We look forward for any feedbacks or any other inquiries or any inputs you need in future. Definitely you are welcome. So you can always write into me, or you can always connect me for any requirements. Thanks a lot for your time.
Thank you, Mr. Dubey. And thanks a lot to our audience for joining us today. We hope you have a great day, and we look forward to seeing you for our next webinar. Thank you. Bye-bye.
Thank you, everybody.